Hello everybody, welcome to YOLO11 notebook. This model called YOLO, you only look once. This is a single shot object detector. What we had learned previously in faster RCNN, it was a two-shot object detection. We learned before there were two stages, so we had to go through getting all the region proposal networks, and then we had to classify them. So that was a two-stage process. This, on the other hand, is a single-stage architecture. And it has a fascinating history. Actually, YOLO started out as not a Pytorch model, but as a darknet model. So darknet is this C library, not even C++. It was a C library. And when it was first released, YOLO v1, darknet from YOLO v1 to all the way to YOLO v4, darknet was the primary C library that people used to use. And then starting YOLO v3, they started porting it to Pytorch and other platforms. But then this company Ultralytics basically took over the development, and there was a little bit of a tension between the people who were maintaining darknet and the people who were the Ultralytics team, because Ultralytics released YOLO v5, and people did not like it initially because the product was really good, the model was really good, but it used the YOLO name. And then, the founder of YOLO, or the person who actually wrote the first version of YOLO, Joseph Redmond, he said that he doesn't care. He stopped working in computer vision because he had ethical issues. He thought that computer vision is such a powerful technique. AI in general is such a powerful technique that it is going to be misused. And I think for those ethical reasons, he stopped working in the field altogether. And he said that he doesn't care who uses the YOLO name. You are free to use the YOLO name as long as you are, helping the community. So he did not care. So Ultralytics basically used the YOLO name. Even now, if you look at all these YOLO versions, YOLO v5 was from Ultralytics. I think YOLO v8 is Ultralytics as well. And YOLO v11, or they actually dropped the V, it is just YOLO 11, is also from Ultralytics. Some of these other models, the other YOLO models, they are not even from the same lab. So for example, the people who made YOLO X, that's a completely different team. And I think YOLO NAS is a completely different team. They are building on the idea of a single shot detector. Some of them started with the same code base, but this is a collection of models. So it's a very funny landscape of models. It almost feels like, it feels like YOLO v4 was created by the same person who created YOLO v5, but that's not actually true, right? Similarly, YOLO v10 was released by somebody else, and YOLO 11 is released by Ultralytics, although YOLO v10 is also available through Ultralytics. All right. So very interesting, right? This whole landscape and the little bit of controversy for the YOLO name. But YOLO 11 is very interesting. Not only is it the state of the art, it actually contains many different models. So for example, YOLO 11N, this stands for nano. This is a very tiny model, right? Only 2.6 million parameters. Then we have small, medium, large, and extra large, right? If you have a bigger machine, you can use extra large or large. If you have an edge device and you want to run object detection, then you can use a smaller model. The price you pay for using a smaller model, it runs fast. That's the benefit. The price is in accuracy, right? It's not as accurate as a larger model. And the accuracy you can see in this thing called MAP, mean average precision, 5095. Actually, don't worry about the name. This is basically a measure of accuracy. We cover all these details, technical details, in our course, Deep Learning with Pytorch. And if you're interested in that paid course, please sign up for it. But just for this notebook, because this is a short course, for this notebook, mean average precision basically is the accuracy of the object detector, right? And you may feel that, oh, 54.7 doesn't look really good, but it's actually very good, right? We are not going to go into the detail of what map means, but 54.7 is a good number. So we get these numbers. It started with 30, the smallest one is 39.5 and the largest one is 54.7. But not only that, we also have to see how fast this thing runs, right? So it basically gives you the inference time, and these are in milliseconds. So if you look at the small model, that takes only 1.5 milliseconds to run, right, on a 640 by 640 image. So extremely fast, right? You can run it even on small devices. So even the largest model on this T4 instance, it actually takes only 11.3 seconds. So these are very fast object detectors. And you can see the performance of YOLO11 as compared to other models in this graph. So this graph is basically showing the latency, right? Which is basically, you can think about it as the speed. And what is the accuracy? Accuracy is in this column. So if you use a small model, obviously you have so latency, the higher number means lower speed. And so here you can see that if you use a small model, of course the speed is very high, but then the accuracy is small, right? And these are the other models. And then it's compared to YOLO V10, YOLO V9, etc., right? So this essentially says that YOLO11 is a very good model. It is the state-of-the-art model. Okay. Then we come to this. I mean, the whole. There are a few other things that are very interesting about this. First of all, I mentioned that it is highly adaptable. There are different sized models for different tasks. But YOLO11, the base model is an object detector, but there are other models that basically do other things. For example, it is trained for object detection, but also for instance segmentation that we learned. So Mask RCNN, for example, was an instance segmentation algorithm. It can be used for classification. It can be used for pose estimation. So pose estimation for a human body means that you're finding certain joints in the human body and you're getting the skeleton of the human body. We'll see an example. And you can also use oriented object detection. So sometimes, let's say you have longish things, right, which are not squarish things. They are kind of long and they are oriented. In that case, you can get a bounding box. If you just use a standard object detector, you can get a bounding box. But that basically, because the object is long and tilted, most of the object is not covered in that bounding box, right? It is inside. The bounding box contains the object, but it's not the right format, right? In those cases, we may want to use oriented object detector, where the bounding box can be rotated. We'll see an example. Now, one of the things that Ultralytics has done, the whole process of using these models, they have made it as simple as possible, okay? So the way to use it is that you simply use pip install Ultralytics. You download all the different images that we are going to experiment with in this notebook. We are just using wget to download them. And then, standard library imports. And this is all the code you need, right? This is all the code you need. So we have a prediction function where we put in the model type, and we'll see, you could use YOLO11 or YOLO V10 and so on and so forth. You give it an image path. You say whether you want to display the results or not so that it can produce the image that you want. And once you pass in the model type, you create the model using YOLO. You simply create an instance of this class using the model type. You get the model out, and then you pass in the image name to the model, and you say whether you want to save or not. And we want to set save to true because we want to display the image, and then the confidence threshold. All right. So here you can see that essentially we are getting all the results, and the results is basically an array of objects. Okay, so we are looping over those, And you can see that first of all, we are getting the prediction image path. We are reading the image as an RGB image, converting it to an RGB image, and then we are simply displaying the image. That is it. And then we pass out the result. So the result is an object that we will see, but the beauty of YOLO is that this implementation of YOLO from Ultralytics is that they have made it so simple for everybody. All the, when you call this, it actually displays the result on the image itself. So you don't have to do this additional work of going and displaying the image. All right. So very simple, as simple as it can be. So here we are putting in the image path, and then we say the model type is YOLO11, and we are using the large model. So this is slightly confusing. This is YOLO11, this one, and then L is for large, and PT is the Pytorch image, Pytorch format, right? Then we call the prediction function, model type, image, display result equals true, and out comes the display. This is it, right? So you can see that it has output this image, right? With all the annotations done already. We don't have to write the code for doing this. And Ultralytics as a company has been doing this kind of thing all the time. Whatever they do, they try to make things as simple as possible for the user. You can also do it yourself, but why not use their annotation? So you can see that it has detected the person class, it has detected sports, the ball, etc. All right, now you can run it again. You take the image of zebra and then run it through this prediction function. And this time we basically want to see what the prediction function looks like. You can see that the output of this results. You get a bunch of boxes. Here we don't get any key points. We'll see when this object is shown. We are not, the mask is none. We'll also see when the masks become important. And then we have the names of the classes, right? Class 0 is person, class 1 is bicycle, car, etc. So all the different classes, they are named here. And then we have this OBB stands for oriented bounding box. This is none. We'll show you an example how we can use oriented bounding box also. And then we have this original image, the pixel values, don't worry about that. You can see that the shape of the image that we sent was 1024 by 1537. And this is, and we got the result, right? We got the result right here. And you can see that the speed, it also splits the speed into all the various components, right? So for pre-processing the image, it took 10 milliseconds. For inference, it took 67 milliseconds. And then for post-processing, it took about 323 milliseconds. And this post-processing includes, right, generating this image where you're drawing on this image. And that is why it takes a little bit of time for generating this image. Now you do the same thing for the zebra image, and this is the result you get. It took 2.5 milliseconds for pre-processing, 37.7 milliseconds for inference, and only 1.3 milliseconds for post-processing. And this could be because the size of the image is small, and also the post-processing also involves something called non-maximum suppression. So if there are a lot of bounding boxes created, it removes the bounding boxes, overlapping bounding boxes. For the same person, sometimes you can get multiple bounding boxes. So it chooses the bounding box which is the most relevant. That is why it is called non-maximum suppression. So that code also takes time. And if it is a crowded field, it will take more time. And you can see here that this one the post-processing for this image was only 1.3 milliseconds because here there are, it's a simpler scene. All right. So again, we take this monitor image, pass it, and you can see it detects the keyboard, it detects the mouse, the cell phone, the person. This entire thing is a person. So you have these overlapping things. All right. Next, it's a kitchen scene. Again, we are able to detect the microwave oven. No, this is the oven, not the microwave oven, just the regular oven. Cups and the refrigerator, whatever is there in that list of objects that we are detecting. Here's another example. We have detected, one cat, one dog, 2 potted plants, as you can see here, and doing a pretty decent job. Okay, all right. Now let's update this function prediction so that we can use it for different tasks. Now you can see that we have the model type and we have added this string here, which is task, right? And this string is this basically the task is we are using this string just to create the title, right? So we are just creating the title here. We are not actually doing anything special, because the model type itself, when YOLO knows what model type it is processing, and it will take care of whether it's a classification model or it's a pose estimation model, etc. So the code is pretty simple. You basically create an instance of the model and then run it, get the results, and display the results. All right. So next, let's do pose estimation. You can see here that we are changing the model. For object detection, the model name was YOLO11L.pt, and here we are appending this name dash pose, and this will select the pose model. Okay, and we do the same image and we pass in the model and we get the inference results. You can see that it is not only displaying the person, it is also displaying the pose of the person. And if you look very carefully, if you look into this, let's open the image in a new tab, and you can see that it is displaying several points on the person's body, right? So these are shoulder points. There are a few points on the face. There are a few points on the hands and the legs, right? So the location of those key points, that is called the pose of an object detection model. Okay, so we can, as you can see, that by changing the model, we were able to change the task that is assigned to it. So YOLO11 will always do object detection. In addition to that, it can do other things also, right? So here we are using YOLO11 seg. So we change the model name and we pass in the same image, and it outputs a segmentation, the segmentation of these models. And remember, we didn't have to do any of these, we did not actually have to do any of this display work, right? This image was displayed, this segmentation on top of the image and on top of this ball, all that work was done inside by the YOLO model itself, right? So we didn't have to explicitly do it. That's why I love Ultralytics. They make things simpler. Otherwise, people would have to, you remember in our previous notebooks, we had to actually create these masks and overlay them, and all that code had to be written. And when you're using Ultralytics, YOLO11, you don't have to do any of that work yourself. Okay. Then we can also use it for classification. So we pass in the class model, right? CLS. And then it does classification. So here you can see it may or may not be visible very easily, but let's open it in a different, and you can see the results of classification. So classification says the various classes, there could be various classes. So it's returning the top 5 classification results, and we can simply select the top one, but you can see that it has top 5. So the Tiger class, it says that it has more than, the confidence is 0.7. You can basically pick the top one, and you can also have a threshold on the top result. If the top one is below 0.5, you could say that, okay, I'm not confident whether the class is correct. So Tiger cat is 0.9, jaguar, another cheetah. So those are very low probabilities, right? So all the confidence is in this Tiger class. So we have done the classification correctly. All right. So the last one is oriented object bounding box. So again, just pass in this -OBB, that's the model name, and then we can, on the ship image, on this boat image or whatever it is, you can do object detection, and you can see here, this is an oriented bounding box, right? So the bounding box that we usually get, it is aligned with the axis, but this oriented bounding box allows you to tilt, and you get a much tighter orientation for this boat. So the question you may be thinking is that, oh, why don't we always do oriented bounding box? It is so much better. It is better, but everything comes at a price. Okay. For example, this calculating the oriented bounding box may be slightly more expensive than calculating just the bounding box, right? And that is why most people use bounding box. And only when there is a special case, when you have these long structures and they are oriented at some angle, in that case, it makes sense to go for oriented bounding box. All right. So that's all we wanted to cover in this notebook. You can click on these links to get all other YOLO models. And you can also check out our course, Deep Learning with Pytorch, which provides you much more details, right? This is a very short course. You can complete this in 3 to 4 hours. The Deep Learning with Pytorch course, it's a good commitment. It's a commitment towards your AI career. It will take you about 3 to 4 months to complete, right? If you're interested in it, go check it out. That's all we had to cover in this video. Thank you so much.